Hello everybody. In the last class we have seen mass energy relationship. We have also seen momentum, kinetic energy, etc. Right? And we know the units of energy, momentum and mass, etc. Right? For example, the SI unit of energy is joule. Right? And for mass we use kilogram, like that. Right? But in the case of systems that we have been dealing in the previous classes, for example, atoms, molecules, and subatomic particles, which are also moving very fast, there is another set of convenient units. For example, for energy, we can use electron volt, okay, and we also have units for convenient units for momentum, mass, etc. Okay, so let us start with the unit of energy, which is electron volt, usually written with small e like this, small e, capital V, electron volts. Okay, so first of all, let us see what is an electron volt, or what is one electron volt. Okay, so let us consider two plates and they are given with a potential, plus here, minus. Okay, so in this case there is a field here, right? Between the plates there is an electric field. So now if we keep an electron or any charged particle here, let's say this is an electron. Okay, so this electron will start moving towards the positive plate, right? So now during this process, this electron will acquire an energy which is equal to QV. Okay, where Q is the charge of the particle electron here, which is 1.602 10 power minus 19 coulomb. Okay, and V is the potential we have applied. So let's say we have applied 1 volt. So when we apply 1 volt, we can take V equal to 1. Okay, so this energy, uh, this electron acquire in the energy this electron acquire in when we apply 1 volt here, that's what we called 1 electron volt. Okay, so 1 electron volt, if we substitute these two values here, we'll get 1.602 10 power minus 19 joule. Okay, so this is what we call 1 electron volt. Okay, so where do we use electron volt? So let us see a few examples. For example, you have probably seen ionization energy, right, in physics and chemistry. So let's say the first example, ionization energy, energy required to remove one electron from an atom, right? So in the case of hydrogen, the ionization energy is 13.6 electron volt, right? You probably know this. Okay, so this is usually written in terms of electron volt, not in joule, not in erg, not in any other units. Okay, so this is the convenient unit. Okay, so another case is binding energy of molecules. Okay, in the case of molecules. Okay, for example, in the case of hydrogen, you can find other examples also. In the case of hydrogen molecule, it is 4.5 eV. If you write it in joule, you will get a very large number. Well, very small number in principle, but the number is going to be, will have powers of 10 and all those. Okay, so this is very convenient here. Okay, so we can also have higher energies like kilo electron volt, it's small k. Okay, so that is 10 power 3 electron volts. Okay, so imagine you are dealing with subatomic particles, nuclear reactions, etc. So in that case, we can have a mega electron volt or even giga electron volt. Okay, so you know this is 10 power 6 eV, right? This is 10 power 9 eV, right? So these are when we deal with, let's say, subatomic particles right? Or nuclear reactions, etc. Okay, so now in the context of our discussion, let us see where we can use these units. Okay, so let's start with the first one, rest energy of elementary particles. Okay, rest energy of elementary particles. Okay, for example, electron is an elementary particle. Okay, so if we take electron, just a moment. Okay, so if we take an electron, the rest energy of an electron is in kilo electron volt 511. Okay, so that is 511 keV or 0.511 MeV. Okay, do not approximate it to 0.5, it is 0.511 MeV. Okay, so this is the energy. Okay, or let's say more accurately, rest energy. Okay, so now we know a mass energy relationship, right? So E equal to mc square, or you can write m equal to E by c square. Okay, so taking advantage of this relationship, we can also write an expression for momentum. Not an expression, we can also write a unit for momentum. Okay, so the unit for momentum is given by MeV per c square. Okay, so these are the two units that we uh, use very frequently. Okay, and we are going to see a few problems involving these two units. Okay, and now so taking advantage of this relationship, we can also write a unit for mass. Okay, so the unit for mass is going to be mega electron volt per c square. Okay, because we have c square here. Okay, so now if we represent the mass of, or if we write the mass of electron in terms of MeV per c square, the mass of electron is going to be mass of electron is going to be again 0.511 MeV per c square. Okay, so now you see the advantage. The rest energy of electron is given by this, and the mass of electron is also given by the same number. Okay, only the unit is different, the number is same. Okay, so when we do a few problems, it will be more clear to you. I mean, the advantage will be more clear to you. Okay, so now we have seen mass and the rest energy. So now let's go to kinetic energy. Okay, so before that, in the case of a proton, it's also it's also an elementary particle. Okay, so I think, what did I write here? Okay, so let's take proton now. So in the case of proton, the energy, rest energy is 0.938 GeV, giga electron volt. Okay, and the rest mass is given by, so this is also rest mass, okay? Rest mass is given by 938 GeV per c square, okay, or 938 MeV per c square, okay. So remember these two numbers, okay, the energy and mass of electron and proton in the new units. Okay, so now let's go to see kinetic energy. Okay, so kinetic energy can also be expressed in terms of electron volt or mega electron volt or giga electron volt. Okay, so we have an example here. Find the total energy of a proton having kinetic energy this much. Okay, 5 giga electron volt. Okay, so the kinetic energy is given. Okay, so we are asked to find out total energy. Okay, we have a proton in hand, so we know the rest energy. Rest energy is 938 mega electron volt. Okay, so the total energy is rest energy plus kinetic energy. Okay, don't mix MeV and GeV. So the rest energy is 0.938 GeV plus the kinetic energy is 5 GeV. Okay, so that's going to be the answer, 5.938 giga electron volt. Okay, all right. So like the case of a mass and energy, we can also get a new unit for momentum. Okay, so in the case of momentum, we know that momentum is E by C. Okay, so let me write momentum here. Okay, so obviously the unit of momentum is going to be mega electron volt divided by C, MeV per C. Okay, or if it is moving with a very high energy, with very high velocity, it can be GeV per C. Okay, so now let us try to write the formula. Just one second. Yeah, so we have a question here. Let's find out the momentum of a proton whose speed is 0.8 c. Okay, so we know the expression for momentum, relativistic momentum. That's what we are talking about, right? So that is m0v divided by square root of 1 minus v square by c square. Okay, so here we can substitute the values. What is m0? We have a proton in hand, so m0 is 0.938 GeV. This is mass, so GeV per c square. Okay, so now the velocity is given by 0.8 c. Okay, so divided by square root of 1 minus v square is v is 0.8 c, 0.8 square c square divided by c square. Okay, so please try to do this yourself. The final answer is going to be 1.25. And what is the unit? You see, this c and this c will get cancelled, so the unit is going to be GeV per C. Okay, you see it is very easy to do the calculation. The C and C cancels and the final unit become very clear, very easy. Okay, so this is the case of momentum. Now let's see one problem from your other basic textbook. Okay, so this is already solved in the textbook, example 1.8. An electron and a photon both have momenta 2 MeV per C. Okay, find the total energy of each. So how do we solve this problem? I recommend you do it yourself. Okay, first try it yourself before you refer to the textbook, and to check your answer, you may refer the textbook. Okay, so I recommend you stop here and do the problem, then you can come back. Okay, so we have an electron. Okay, and a photon. Okay, okay, so in the case of photon, m equal to 0. Okay, here m0, it is m0, right? m0 is 0. Here m0 is 0.511, so this is actually m0. Something, it's a mistake. MeV per C square. Okay, so both have the momenta. E is given by 2 MeV per C. Okay, find the total energy in each case. Okay, so we have an equation that relates total energy, momentum, and rest energy, right? What is the relation? E total square equal to E square C square plus M0 square C power 4. Okay, or you can write E equal to square root of this. Okay, so we can directly substitute. P is 2 MeV per C. Okay, so 2 square. Okay, MeV per C square multiplied by C square. Okay, plus M0 is 0.511 MeV per C square. Okay, so M0 square, right? So this square multiplied by C power 4, square root of all this. Okay, so now if you try to simplify this, what do you get? So this C square will go with this C square. Okay, so this is 4 here, and here this C power 4 will go with this C power 4. Okay, so we will end up with so now you can simplify. So this is the advantage of using these units. Okay, so we don't have to, basically you don't have to substitute for C square. Okay, for MeV square plus 0.511 square MeV square. Okay, so now you can take MeV square outside, that will become unit of energy MeV. Okay, so please do the calculation. I think the answer is 2.064 MeV. Don't forget to write the unit. Okay, so now, so this is in the case of a particle like electron or proton or whatever. Okay, now the second particle is a photon. We know that its rest mass is 0. Okay, so in that case, equation for energy is equal to Pc. Okay, P is given by 2. What is the unit? MeV per C. Now you have C here multiplied by C. You see, you don't have to substitute for C because it will get cancelled directly. Okay, again I repeat, that is the advantage here. Okay, so the energy is going to be 2 MeV in this case. Okay, so your calculation is very simple. Okay, because of the new set of units. Okay, so please watch this video and go through the corresponding sections in the textbook. Okay, and tomorrow we'll be continuing from here. Okay, so if you come to tomorrow's class without going through this, you will be getting confused. Okay, so to save time, I recommend you watch this video and try to solve corresponding problems also in the textbook. There are so many problems. Okay, we'll see a few. Okay, but we won't have time for solving all the problems. Okay, okay, so I'll see you tomorrow. Bye bye.